Okay, so let's get back into finishing up cyclic alkanes. We're looking at how to name them. Okay, so when you had two groups on a cyclic molecule, we could draw them one of two ways. Okay. We could draw them on the same side of the ring or on opposite sides of the ring. Okay. Another way to symbolize this, as you can see, trying to draw this is a little bit hairy there. We could also draw these like this. Where if they're on the same side of the ring, I use these two wedges, okay? Two of the same wedges. Where if they're on opposite sides of the ring, I can use a wedge and a dash, okay? So I use opposite things here to show they're on opposite sides of the ring. So if they're on the same side of the ring, this is your cis isomer. If they're on opposite sides of the ring, this is your trans isomer. Okay? So this one over here would be called cis 1,2-dimethyl cyclobutane. Okay. And this one over here would have the exact same name, except what? You have the trans in front. Okay. So these two are isomers of each other, and the way we designate these special kinds of isomers are by cis and trans. Okay. You cannot convert the cis to the trans. These rings are stuck. You can't rotate in a ring. So if it's cis, it stays cis. If it's trans, it stays trans. Okay, so these are two different molecules. Okay. So we can do this cis-trans. We'll typically stay with the dashes and wedges to show this kind of thing. We can show this on other molecules. Okay, we can show it on cyclohexane, for example. Okay, we can put on two different groups. Okay, the 1,3 relationship, or even in cyclohexane. Okay, these two groups would be cis to each other, and they're on the 1,4 carbons from each other. Okay, so you should be able to now tell and explain what these dashes and wedges mean in terms of how the two groups are related to each other. Okay, So any questions on cis and trans, how to deal with those? Okay. Okay, well, let's look at cyclic alkanes in a little bit more detail. Here are a series of cyclic alkanes all the way up to cyclohexane. Okay? We want to look at the energies of these things. How stable are these things? Okay? Well, these molecules, when you get to cyclic molecules, can have what are called ring strain. Okay? So because a molecule is cyclic, you can have strain associated with it. Okay? So what's going to contribute to the strain of the cyclic molecule? Well, remember all these carbons are sp3 carbons, aren't they? There's no double bonds, no triple bonds. Okay? And remember that the bond angle for sp3 carbons is 109.5. Okay? So a big deal. Well, here's the big deal. If you look at this triangle, what is the bond angle in that triangle? 60 degrees. Okay? So this angle here is 60 degrees. Is that close? Is that 109.5? No, it's pretty far away, isn't it? So here, the ring strain is caused by what we can call angle strain. Okay, so angle strain is the amount of deviation from 109.5. Okay, and so we see that we're over 40 degrees away from a sp3 angle carbon. It wants to be 109.5, and we got 60, so that thing has a lot of strain to it. Okay? Same thing when you come to cyclobutane. That angle is just about 90 degrees. Okay? So not as much strain as the cyclopropane, but it still has some. Okay? So you would predict cyclopropane and cyclobutane to not be very stable molecules. In fact, cyclopropane, these bonds are so strained, okay, you can read about it in the book, they're so strained, they're bending, and they're dying to break. And if bonds are dying to break, it kind of makes the molecule explosive, okay? So cyclopropane is so strained, it's explosive. Those bonds are just dying to break apart to alleviate that strain, okay? Well, as you continue up, cyclopentane, the angles get a little bit better, okay? But the magic one is cyclohexane. The bond angles of cyclohexane turn out to be 109.5. So you predict what? Cyclohexane to be the most stable out of these rings. Cyclopentane's pretty stable too, okay? It's very, very close to 109.5. But the absolutely most strain-free is cyclohexane. And it's not surprising that in our bodies, cyclic molecules in our bodies are mostly cyclohexane molecules. Okay? For example, cholesterol is a molecule made up of a couple cyclohexanes. And we all have cholesterol in our bodies. And so, okay? You would never find a cyclopropane in our body, okay? That would not be good, okay? So what we're going to do, since cyclohexane is the most stable, we're going to focus on that and see some more interesting properties with it. Okay? cyclohexane actually does not exist in that flat structure that we just had, but it exists in this three-dimensional structure like this. Okay? And this three-dimensional structure, it kind of looks like a chair, doesn't it? Okay? So this is what's called the chair conformation for cyclohexane. When cyclohexane gets in this chair, all of the angles are 109.5. Okay, so that's one of the reasons why it adopts this chair conformation. Okay? Well, let's look at the hydrogens on this chair conformation. Okay? So these hydrogens are going to exist on one of two types of bonds. Okay? You want to get used to drawing these bonds. Okay? So if you take a look at how I drew them, this one here, I drew up, straight up, then the next carbon, it went straight down. Then this carbon, it went back straight up, then this carbon, back straight down. Okay? And the ones that aren't going up or down, they're always going out to the side. Okay? See that? So you want to get used to drawing these things, and the hydrogens are going right on these bonds. So let's put them on. Like that there. Okay. So there's our 12 hydrogens on cyclohexane. Okay. Well, the hydrogens that are on the bonds going straight up or straight down, these are what are called axial hydrogens. Okay? So remember, axial hydrogens are on the bonds going straight up or straight down, like the axis of the Earth. Okay? So you get axials there, and there, axials. Okay? So you'll have a total of 6 axial hydrogens, one for each carbon. And then the other bonds, they're not axial bonds, they're what we call equatorial bonds. Okay? So equatorial bonds are like the equator, they go out to the side. Okay? So think of the axials like your north and south pole. Okay? So we got 6 equatorial bonds as well. Okay? Again, I won't label them all, but just to give you a sample of them on the molecule. So any questions on what axial and equatorial bonds are? Okay? So let me erase them and kind of clear the picture here. One of the things that cyclohexane likes to do is do something called a ring flip. Okay? When it does a ring flip, what happens is this carbon down here that's at the feet, it's going to come up, and this carbon at the head is going to come down. See that? So the ring flips on itself. Okay? And when the ring flips on itself, something interesting happens. Let's look at this carbon here. Okay. So this carbon that's now at the feet was this carbon that is at the head. Okay. And the bonds, this hydrogen here was axial. If I follow it over here, it's now equatorial. Okay? So here we find an important principle of ring flips, that axial becomes equatorials, and equatorials become axials upon ring flips. Okay? So now you should be able to draw ring flips of cyclohexane and know the important property that anything that was axial becomes equatorial upon that ring flip. Okay? Okay. Well, one of the things in this ring flip, it doesn't actually just flip immediately. It goes through kind of a transition state, and that transition state that will sometimes draw, but not all the time, is where the two ends of the chair actually are pointing up before it goes to the other chair. In this intermediate state is sometimes called the boat conformation, because it looks like a little boat. Okay. And so the boat forms, and then it goes over to the chair. Okay. So this boat conformation is actually a higher energy state than either of these chairs. Okay. In the chair, there is no ring strain at all. Why? Again, there's no angle strain. And also, if you look down any bond axis, say this bond here, the hydrogens are perfectly staggered. Okay. So write it down. Cyclohexane, there is no ring strain for two reasons. One, there's no angle strain, they're all 109.5. And two, there's no eclipsing strain, or what was that called? Torsional strain. There's no torsional strain because these hydrogens along any bond axis are perfectly staggered. Okay. In all the other rings, they will either have angle strain or torsional strain. Okay, those bonds can somewhat get a little bit closer to each other. Okay, but not with cyclohexane. But in the boat conformation, you lose this low energy state. Okay, that these hydrogens at the top here they can get a little bit close to each other to the point where you don't have this staggered anymore, but they can start to become eclipsed, okay? So the boat is a higher energy conformation than the chair. but it goes through this in order to go from one chair to the other, okay? All right, well, let's go into cyclohexane chairs a little bit more. Let's look at this molecule, methyl cyclohexane, and let's make the chair conformation of it. So there's the chair. Maybe you're finding it's difficult to draw that, but it gets easier with practice. And we want to put on this methyl group. Let's choose any carbon to put on that methyl group. Doesn't matter. Now if I come to a carbon, I got 1 or 2 bonds to put on the CH3, the axial or the equatorial. And it doesn't matter which one I put it on. Let's just make a choice. Let's just put it on the axial. Okay. But now, once I have that axial and I do a ring flip, where's it going to end up? On the equatorial. Okay. So again, it was on this carbon, so it's going to stay on this carbon. This is one of the things students run into trouble with. They sometimes move the group to another carbon. You got to keep track of which carbon it's on. So here it's on that carbon. So now it was axial, but here it comes equatorial. Okay. Another way to keep track of this is if you draw an imaginary line like that, what side of the line is that CH3 on?
Right.
The top or the bottom? The top. So when I draw this imaginary line here, it better stay on the top. And is it on the top? It is, okay? So it's on the top here, it better stay on the top here, okay? Only thing that changed is it went from axial to equatorial, okay? Well, as soon as you put on a non-hydrogen group, remember the size of the group increases, doesn't it? So that now, this bigger CH3 can start feeling a little bit some of the interactions from those hydrogens that are axial at the other part of the molecule. And this introduces what's called 1,3 diaxial strain. Okay? So if the group is in the axial position, you get some of that strain. So which chair conformation would you predict to be the more stable conformation? This one here, where the equatorial is, or this one here, where the axial is? Which one would be more stable?
Second one.
Why would the axial be more stable when I just told you it has strain? It would be this one here. Okay, so when I put the group in the equatorial, it gets away from this strain. Okay? So if I have a group in the equatorial position, it alleviates what? This 1,3 diaxial strain. Okay? So this chair would be more stable than this chair. Okay? Any questions on that? Get that out of your system. Okay? Okay? Let's do another one here. Okay. Now let's put on two groups on cyclohexane. This is when it gets a little bit more interesting. Okay. So if I have two groups, what's the relationship of those two groups? Are they cis? Okay, good. Okay, I want to hear trans, not opposite. I want to hear trans. Okay. So let's put them on the ring. For the chair conformation, this is always the hardest part for the student. Okay. And these two CH3s are on what? Adjacent. There. Doesn't matter. I could have put it on the equatorial position. I just like to first of all start it off axial. It doesn't matter though. Okay? But let's be consistent and put it there. Okay? So it also has the hidden hydrogen, so we'll put it there on the other bond. Now I want to come down here and put the other CH3 on it. Where is it going to go? On this bond or on this bond? Let's figure it out. This is where students always mess up. Just like you did. Come back to our imaginary line. What side of that imaginary line is the CH3 on? Top. Okay, pretty easy. There's my imaginary line down there. What side do I want to put the other one on?
The top.
The bottom, the opposite. Okay? So the trans tells you, write it down, on opposite sides of the line. Has nothing to do with equatorial and axial. It only has to do with the side of a line. Top or bottom. Don't forget it. So, since they are trans, I will put them on opposite sides of the line. Okay? Okay. Any questions on that? So now you have the right relationship on the cyclohexane ring. Okay? Now we can do the ring flip. Okay? So upon doing the ring flip, make sure that you follow your two carbons there. And make sure you draw the bonds correctly there, okay? So this CH3 was axial, so now it's on the equatorial bond, like that. And notice that it still stayed on the top side of that line. Okay? So don't switch it down here where you get 0 points. Keep it on the top side of the line. And this CH3 came where? Now it is equatorial, and it is still staying on what? The bottom side of the line. Okay? So keep your relationships always priority first. Okay? Any questions on what we just did there? Ask it now. Yeah.
Is there a reason why you didn't put, when you did the flip ring, the other CH3 like on the back side?
Okay? Because this, I'm keeping it on this bond here. Okay? Leave this carbon alone. We didn't use that. That one's there. So I'm using these 2 front carbons here. Okay? So that's a temptation. Students switch it back there and then they mess up. Any other questions there? Okay. Well, now, after we got the relationships right, now we talk about stabilities. And I think you can answer this one. Which will be more stable, the left one or the right one?
The right one.
Why will the right one be more stable?
Left one.
On the equatorial.
Because what? They're both equatorial. Over there, they're both axials. Axials are bad. Okay? So here, both groups are equatorial. So this will be the more stable ring, or the more stable cyclohexane. Okay? So remember, axials are higher energy. Why? Because of the 1,3 diaxial strains with the hydrogens there. Okay? So the equatorials, I always want to choose those if I can. And here, it gives me both equatorials. So that's an easy choice as to which one's more stable. These are both axial. The carbon did not move. That's why I draw these dots, to show you the 2 carbons in between, okay, that we're focusing on. Okay? So this one came down, and so this CH3, by definition, will become equatorial. Okay? All right? So we'll do some more examples, and they'll become more clear in practice. Okay? All right, let's do another example. You might say, well, yeah, this is easy if I can get both groups to be equatorial. But what happens if one group is equatorial and the other group is axial? See that? Let's take a look at something like that. Let's take a look at this molecule. trans there. Okay, so since they're trans, they're going to be on opposite sides. Okay, again. So the 2 carbons we're going to focus on now are the 1 and 3 carbons. Okay? So I'll let this one be 1. I come down to 3, so 1, 2, and now 3. So I'm going to use this one here. Okay? So let's put on the groups. On the 1 carbon, I have this methyl. And again, let's just put it on axial to start with. It doesn't matter, let's just choose axial. The 2nd carbon does not have any groups on it, so it just has 2 hydrogens. The 3rd carbon now has the ethyl. Where is the ethyl going to go? On this axial or on this equatorial?
Equatorial.
You see it? Okay, right, it'll be the equatorial. Let's make sure we follow. There's our line, so that one's on the top. So now, over here, here's my line. So I want this ethyl on the bottom. Okay, so there it's on the bottom, like that. So now I have my trans relationship. Okay. Once I have that set up, now I can do my ring flip. Okay, so if I do my ring flip, again I bring my head down, which is this carbon, and the other carbon is now right here. So now my head carbon, there are my axial and equatorial bonds. Now the CH3 is going to be where? Equatorial. Again, I can use my dotted line to still show it's on the top. Okay. There's those 2 hydrogens that are not a big deal. And now let's come to the 3rd carbon. The 3rd carbon, now the bottom has become axial, where it was equatorial. So my ethyl is still on the bottom, but it is now on an axial bond because of the ring flip. Okay. All right, let me answer some questions.
The part when you flip it, why is it not like in the vertical?
What's that? Yeah, come on.
Wouldn't these got to be right here?
Okay, so what I'm doing here, okay, this is something always students get confused on, so I'm glad you're asking it now. Kind of use a dark line here. These carbons are coming out in the front of the ring. So that's what these are here. Okay, so that bond axis is out in front. this bond axis is behind, okay? So we'll leave this alone, we didn't use that, I just used this front part, okay? If you come to my office, I'll show you a cyclohexane molecule, and I can show you in more detail using the molecule, okay? Any other questions on what we drew there, okay? All right, so now, after we do that, that's the hard part, getting the two cyclohexane chairs right. Now we ask, which one is more stable? Well, here, we got axial and equatorial. Here we got equatorial and axial. So I don't need to pay attention. I don't have a case where I have them both equatorial. So what do? What I do now is I choose which one is the bigger group, methyl or ethyl. The ethyl's the bigger group. And by definition, write it down, I want the bigger group on the equatorial. Okay, so you look for the bigger group on equatorial to be more stable. So which of these two chairs will be the more stable?
The first one.
The first one. Okay, so that's how you handle if two groups are equatorial and axial. Look for the bigger one, and I want the bigger one on the equatorial one. Okay? Any questions on that? Okay. All right, so this finishes up the cyclohexane, and it finishes up the chapter. Okay, so get on these cyclohexane problems immediately. Okay, and also in the recession groups for next week, okay, whether you meet Monday or Wednesday, okay, if you can go to the Monday groups, okay, if you're on a Wednesday, that would be good, because there's an exercise we're going to do that gets on this stuff, cyclohexane, and also your Newman projections, because your exam is going to be Wednesday, okay? So if you can come Monday, do it. If you can't, so be it. Question?
But I mean, if we're not having the Wednesday.
Yeah, you'll still have the Wednesday group. The exam will be between 3 and 5. So if your session is at 3 or 4 o'clock, you'll have to go to another session. That way, that's the reason I'm saying if you can go to the Monday, that's when you can do that. You'll have a quiz next week as well. So if you can get it Monday, get out of the way, and get it straight from there. You got your graded quizzes up here.